Beneath the Black Hills of South Dakota, an elevator descends through a mile of ancient rock. The rattle of the cage fades. As the air cools, voices drop to a whisper. At the bottom waits something that looks less like a physics experiment, and more like a cathedral to silence, a vat of liquid xenon, cold and clear as melted moonlight. Around it, photomultiplier tubes bloom like mechanical flowers, poised to catch the faintest glimmer imaginable. Here, scientists wait for a trespasser that may never arrive, a weakly interacting massive particle, the WIMP. The idea is disarmingly simple. Take a particle no one has seen, give it the heft of a heavy atom, yet make it so aloof that it slips through planets as starlight slips through glass. Scatter enough of these invisible travelers throughout the cosmos, left over from the Big Bang, and their collective gravity could explain why galaxies spin too fast and clusters cling too tight. But aloofness is a double-edged trait. A WIMP might traverse a light year of lead before striking even once. That is why detectors such as LUX-ZEPLIN and xenon burrow deep underground, far from the hail of cosmic rays that pepper Earth's surface. Should a WIMP bump a xenon nucleus? The atom will recoil and flash just a handful of ultraviolet photons, a cosmic knock at the door. Every minute, supercooled electronics sift the darkness for that tiny pulse, amid a sea of radio-quiet calm. Years of watching have yet to reveal a definite signal. Each null result shrinks the range of possible masses and strengths, like tightening a net around an unseen swimmer. Still, optimism lingers in the corridors. After all, nature rarely gives up her secrets on the first polite request. Yet if the universe favors subtlety over muscle, its missing mass could lie not in heavyweight loners, but in countless wisps so light they drift like cosmic pollen. Axions await in the next chamber of our search. Imagine an old-fashioned radio, the kind your grandparents tuned with a brass dial. Instead of music, picture that receiver, listening for a single, pure note, sustained since the dawn of time. This is the essence of an Axion haloscope, a resonant copper cavity cooled near absolute zero, shielded from every earthly broadcast, and cradled within a powerful magnet. Its purpose: to catch a whisper from particles so light they make an electron look elephantine. Axions were born on paper in the late 1970s, conjured to mend a flaw in the theory of quarks and gluons. Quite by accident, that same fix endowed the new particle with properties perfect for dark matter. Immense abundance, vanishing shyness toward ordinary matter, and an almost magical ability to transform into a microwave photon. When passing through a magnetic field, like a silent violin string that suddenly resonates inside the right concert hall. Inside the ADMX experiment in Washington State, engineers scanned the cavity's tuning rods micrometer by micrometer, shifting the resonant frequency much as a listener sweeps the FM band. At each setting they linger, hoping that an axion from the galactic halo will drift in, feel the magnetic field, and sing its single-note photon into the detectors. A triumph would appear not as a bright flash but as a hair-thin peak rising from background noise. Evidence that empty space is in fact saturated with invisible melody. Beyond the laboratory, axions may already hint at themselves. Some aging stars cool faster than models predict, as though an extra vent in their fiery furnaces leaks energy in axionic form. Elsewhere, astronomers track the flicker of magnetars, whose colossal fields could coax axions into light right before our telescopes. Between the heavy WIMP and the featherweight axion lies a middle path. Particles warm enough to roam, but light enough to slip through early cosmic webs. Sterile neutrinos shall step onto that path in our next exploration. Neutrinos are the wallflowers of the particle family, born in nuclear furnaces, streaming through planets as though through mist. For decades we counted 3 kinds, each partner to a charged lepton, all so light they barely register on gravity's ledger. Yet hints from oscillation experiments and reactor anomalies suggest a shy fourth cousin might linger just beyond the spotlight: the sterile neutrino. Unlike its sociable kin, a sterile neutrino would ignore the weak force entirely, conversing only through gravity and the faintest whispers of mixing. Give it a mass of a few kiloelectron volts. Heavier than ordinary neutrinos, far lighter than WIMPs, it becomes warm dark matter, agile enough to blur the smallest knots in the cosmic web, but still massive enough to sculpt galaxies. Astronomers search for its calling card in X-ray skies. When a sterile neutrino decays, it should emit a photon about half its mass and energy. In 2014, telescopes peering at galaxy clusters spotted an unexpected line near 3.5 keV, a spectral hairline fracture that refused easy explanation. Some hailed it as the sterile neutrino's first public statement. Others cautioned that tangled astrophysics can imitate subtle lines. New missions like Axion and Athena will soon sweep the heavens with sharper eyes, testing whether that slender spike is genuine or a mirage. On Earth, beta decay studies tighten the net. Experiments such as Katrine weigh the tail of tritium's energy spectrum, hunting for the tiny kink a sterile neutrino would leave behind. Each null result prunes the parameter space, yet a tantalizing pocket remains, just large enough for a particle that could ease long-standing puzzles like the scarcity of dwarf galaxies or the smooth cores of dark matter halos. But suppose we never catch any particle at all. Could gravity itself be wearing the wrong glasses? In the next section, we revisit bold attempts to tweak the very law Newton and Einstein bequeathed, testing whether darkness is a missing mass or a misread map. Step onto a high plateau at night and trace the arch of the Milky Way. Its spin, Vera Rubin showed us, is too swift for the visible stars to stay bound. One remedy is extra mass the dark matter we've been stalking. Another is more daring. Perhaps gravity grows stronger on galactic scales than our equations allow. Enter modified Newtonian dynamics, or MOND. Proposed by Mordechai Milgram in the early 1980s, MOND tweaks the familiar formula of Newton's second law of motion. When the acceleration drops below a whisper, about a 10 billionth of a meter per second squared. With that single adjustment, the flat rotation curves of spiral galaxies emerge naturally, no unseen matter required. It was an elegant bandage, and for isolated galaxies it fit astonishingly well. Yet galaxies do not live alone. In rich clusters, the MOND correction still falls short. Gravitational lensing around those clusters maps more pull than visible mass plus MOND can muster. Cosmic microwave ripples pose a sterner test. The pattern of peaks demands. A universe whose inertia budget is dominated by something non-baryonic. To keep pace, theorists built relativistic cousins like Teves and Eric Verlen's emergent gravity, adding fields and phases in hopes of matching lensing in the early universe without dark matter. Thus far, observations from Planck, weak lensing surveys, and the bullet cluster keep tipping the scales toward an invisible substance rather than a rewritten rule. Still, modified gravity ideas refuse to vanish. They serve as intellectual probiotics, forcing the community to double-check assumptions and sharpen instruments. The debate has steered fresh observations such as ultra-diffuse galaxies, wide binary stars, gravitational wave propagation that could yet reveal cracks in the orthodox edifice. Whether we chase particles or polish theories, the hunt now widens to every messenger the cosmos offers, from radio pulsars to ripples in spacetime. Our next step explores this multi-messenger frontier where dark matter may finally betray its presence in stereo. For most of scientific history, we studied the universe with one sense: light. Today, new senses are awakening, and each offers a fresh path toward the unseen mass. Think of the cosmos as a grand orchestra. Photons play the violins, but now neutrinos add their subtle woodwinds. Cosmic rays crash like cymbals, and gravitational waves rumble the deepest bass. By hearing the full score, we may at last isolate the quiet theme of dark matter. Begin with pulsar timing arrays, dozens of millisecond pulsars scattered across the Milky Way, each flashing radio beats with atomic clock precision. If a clump of dark matter drifts between Earth and a pulsar, its gravity tugs on spacetime, delaying the pulses by billionths of a second. Combine data from many pulsars, and those minuscule delays line up like dots in a connect-the-stars puzzle, sketching the mass and motion of the intruder. Projects such as Nanograv and the coming SKA telescope now monitor hundreds of pulsars, turning the galaxy itself into a gravitational detector. Farther afield, merging black holes and neutron stars broadcast gravitational waves. As these waves traverse the cosmic web, they may pass through dark matter halos, picking up tiny phase shifts or lensing distortions. Next-generation observatories such as LISA in space and Einstein telescope on Earth will measure those subtleties, offering a new map of mass unlit by stars. Even high-energy particles join the search. Cosmic ray detectors like AMS ride the International Space Station, counting excess antiprotons that could drip from dark matter annihilations. Neutrino telescopes buried in Antarctic ice hunt upward-going flashes, possible echoes of dark matter decay deep within the sun. What unites these diverse messengers is complementarity. A signal in one channel can be noise. The same signal echoed in 2 or 3 becomes a revelation. By weaving radio pulses, space-time ripples, and charged particle showers into a single tapestry, scientists hope to triangulate a shadow that no single eye can see. Yet even if the riddle of dark matter yields, half the cosmic ledger remains unbalanced, mysterious pressure driving space itself to stretch. In the next part, we turn from hidden pull to silent push and meet the enigma called dark energy. Our journey through the dark matter labyrinth has carried us from galaxy rotations to colliding clusters, from xenon vaults beneath mountains to radio beacons scattered across the Milky Way. Each clue, whether a missing satellite, an X-ray whisper, or a pulsar's late heartbeat, tightens the outline of an unseen companion that outweighs every shining star 5-1. Yet even as we refine that portrait, the universe reminds us there is another, deeper mystery at play. Look past the local groups and glittering superclusters, and you find the cosmos itself expanding. No surprise, since Hubble. But measure carefully, and the expansion is not slowing under gravity's grip. It is accelerating, as though all of space inhales a steady, unseen energy. This silent push is not a fringe footnote. It dominates the cosmic budget more decisively than dark matter dominates galaxies. We call it dark energy, but the name is a placeholder, a marker for something we do not yet understand. Where dark matter pulls structures together, dark energy drives them apart. One sculpts the cosmic web, the other stretches the web's frame. They are the twin shadows of modern cosmology, shaping everything, from the size of a child's telescope target to the ultimate fate of time itself. So we pivot to the next chapter. We'll trace the discovery of cosmic acceleration, follow baryonic sound waves frozen in the galaxy distribution, and confront the vacuum paradox that pits quantum theory against observation by 120 orders of magnitude. Prepare to meet a force that acts everywhere, on everything, yet offers no handle to grasp. Only the quiet conviction that the universe is still rewriting its own expansion script. Join us in Part 4 as we listen to the supernova that first whispered the news, and feel the subtle tug of a darkness that does not pull, but pushes.